Welcome to OpenFlow Fundamentals Part 1. My name is Dustin Burns, and I'll be guiding you through the basic concepts of OpenFlow and how it applies to the realm of SDN. You can think of this class as the 1,000-yard view of OpenFlow, while Class 2 digs deeper into the concepts touched upon in this class. So let's begin. First we'll go over what rib, fib, and TCAM are, and why it's important to know how they relate to OpenFlow. After that we'll touch on the three core SDN concepts and how each one is important. And we'll also go over how the switch handles packet processing and finally state distribution. So would you like some ribs with your fibs? I know, really bad joke. I'm sorry, put you guys through that. Let's just go forward. Fibs come from ribs. So fibs or forwarding information base comes from ribs or routing information base. The routing table is reformed into an ordered list with the most specific route first for each IP destination subnet in the table. This new format then becomes the fib, so to restate that, your rib will find the best route or best valid route and place it into the fib. Your fib will contain the layer 2 encapsulation data to get it to the next hop at wire rate. So today's networks contain the control plane, the data plane, and the management plane. The control plane is the one that consists of all the complex software that calculates your routes, defines routing paths, runs complex algorithms, processes the requests and punts from lower layers, and so on. The problem with this being on every device is that one of the devices has its own view of the network based on what it gets from information from its neighbors or group members. The idea with SDN is to take this complex software off the devices themselves and host it from more centralized controllers. The controllers will have a much better idea of what the network looks like, and this will be explained further at the end of the class. With this information, the controllers will update the clients, which then updates the fib, which populates the forwarding actions. So I tend to like to repeat myself, so I put most of that here again. We want to extract the control plane from the data plane, get it up to a server of some kind or appliance, and implement or install a client on the device itself to talk to the controller. We want centralized or decentralized controllers that contain a global view of the network topology. This will be the point where your control applications can be run against your network. And finally, we want to be able to implement a vendor-agnostic protocol to allow the controllers on the client on the switch or forwarding target to talk. So if you speak English, some of you speak Spanish, you guys aren't really going to have a really great conversation. So you both have to be using the same language. This is where OpenFlow comes in. So I like pretty pictures. They help me learn quick, so I just kind of threw this in there as well. So again, with the simple idea of we're going to be extracting the control plane off of the device. I'm going to move it into an OpenFlow controller and then replace the controller on the device with an OpenFlow client. So in this video we're going to focus on OpenFlow version 1.0. It was the first official and stable release, and it came out in December 2009. It included a basic QoS queuing mechanism for mapping flows to multiple queues. This allowed each queue to be allocated minimum bandwidth guarantees. It also supports the QoS IP types of service, or TOS for short, differentiated services code point, or DSCP. Slicing was also introduced, which was used to allocate a slice of the network bandwidth. Slicing is used for guaranteeing minimum bandwidth for queuing. It's called slicing because essentially it's a slice of your available network bandwidth. FlowVisor describes slicing in a different way, so just not to confuse you, it pertains to flow space. This pertains to your bandwidth, but we'll talk about that later in the series of videos. Next, we see cookies were added as an extension to the flows. The cookie is an opaque value that can be used to filter your flow statistics, flow mods, and flow deletion. They can be queued and returned with flow expires. Instead of maintaining a lot of state on the controller, this makes it easier to allow applications running on the controller to take action based on what is in the cookie field. This comes in handy when you can correlate flows across multiple switches by checking a single identifier as opposed to correlating all the possible tuples in a flow. The ability to query port statistics for individual ports on a switch was added as well, rather than having to query all the ports and parsing out all the individual ports on the return. What is CAM and TCAM? Simply, the binary CAM or BCAM searches for an address. If it's found, it returns a 1. If it doesn't, it returns a 0. So it's either there or it's not there. The ternary CAM or TCAM adds a do not care bit or a wildcard bit. It usually shows up in tables as an asterisk. TCAM can have multiple matches and it can determine a best match. So what does TCAM have to do with SDN? Well, since vendors at the time were not providing OpenFlow enabled hardware, we needed a way to get packet flows into the OpenFlow pipeline. In order to get this to work, it required flexibility in the forwarding tables. So early adopters of OpenFlow use TCAM to insert a flow of the forwarding information base. You can read a lot about TCAM. It's very interesting. I recommend at least looking at a wiki on it. But we're not going to get too deep with it. Just know that TCAM was being used as a mechanism to get non-OpenFlow enabled switches able to process flows. Now let's take a look at what the flow table's job is in OpenFlow. When the switch first receives a packet, it looks at various fields in the header. Layer 1 through 4 information is checked against the flow table in order to find a match. If a flow already exists on the switch for that packet, it's processed with the associated instructions. For example, it can be forwarded out one or more ports, it can be modified and then forwarded, or you can encapsulate it and send it up to the controller, or just simply drop it. In this case, we're concerned with version 1, so the default action for an unmatched packet in version 1 is to forward it to the controller. Depending on whether you have the flow table updated proactively or reactively, which we'll get into later, it could cause a lot of chatter between the controller and the client. So each flow table is made up of flow entries. Like any other type of forwarding table, each flow contains 3 key fields: the match field, the counters field, and the instruction or the action field. Match fields are used to match against packets as they consist of ingress ports and packet headers. Pretty self-explanatory here. This is what targets the interesting traffic, and in combination with the next field decides on what to do with it. The counters field is used to update on how many times a packet was matched by the match information. And finally we have the instructions field. This field will modify the action set or piping processing. This is basically telling the packet where it should go, if it should be rewritten, or any other predetermined action for the flow. In newer versions of OpenFlow, this could also tell the packet to get processed by another flow table, but we'll get into that later on. Grasping these core concepts is very important though. Now let's take a look at some of the actions we have to choose from. All will process the packet like an unknown unicast, so basically it'll send it out all ports except for the one that it came in on. Controller means that it will encapsulate the packet and send it up to the controller for processing. We see local will send it to switches, the switch's local networking protocol stack. Table performs actions on the flow table itself. This is used with packet out, which is explained in the next class. Import or in space port means you're going to send it out the input port. These first two are optional actions to take on an OpenFlow enabled switch, as opposed to OpenFlow only switches. Normal means that it will be processed by using the traditional forwarding path. This, for example, can be used to get your SDN switches to your non-SDN switches. Flood means to flood along the minimum spanning tree, not including the incoming interface, and drop will drop the packet. A flow with no action specified will result in a drop. So logically speaking, we get a packet in from the network. STP will be consulted, and then the header will be parsed for information. It then comes to the first table, in our case the only table, and searches for a match. If using the newer versions of OpenFlow, you can send it to the next table, shown here in match table N. So if there's a match, then we apply the actions. If no match, then it's sent to the controller for processing. Let's take a look at a sample flow table. To keep it simple, I don't have the ingress port, the VLAN ID, VLAN priority, IP protocol, or IPTOS fields, which are included, but for simplification, I've taken that out. So we see here that the first flow entry is to match a packet that has a destination MAC of PC1's MAC and a destination IP of PC1's IP. The action of this match will be to send it out interface 101/1/4, as you can see here. And we also see here the counter. Next we see a more specific match, where we're looking at both the source and destination MAC and IP. We're also catching traffic with port 69, which is TFTP, and dropping it. And of course we have the counter. So here we have a packet that is coming into a switch. It's brought into the ingress queue, and then it gets processed and sent to the table for a lookup. After finding a match and receiving what the action should be, it's sent out the egress queue, or it's sent to the egress queue to wait for transmission. In this case, the action was to send it out of interface 7 with the destination of interface 2 on switch 2. Again, the packet is brought into the ingress queue, gets processed and sent to the table for lookup, and after finding a match and receiving what the action should be, it's sent to the egress queue to wait for a transmission, in this case sent out interface 5 to its next destination. So now let's take a look, let's talk about the ways that you can distribute your flows. The two main ways to do this is by either using proactive flows or reactive flows. As you'd guess, proactive flows are pre-populated on the switches ahead of time to reduce the number of times the client needs to send the packets up to the controller for processing. Which brings us to the next method, reactive. Reactive takes a packet, compares it to the flow table, and if it doesn't find a match, it gets encapsulated and sent up to the controller. To update the flow table on the switch for future packets, a controller will send a flow mod, or a flow modification, down to the client to update its flow table. Depending on how much you know about the network, or even the size of the network, will most likely steer you in one of these two directions. But another approach would be to implement a hybrid distribution. This is a combination of proactive and reactive, and it leverages the reactive approach for a more granular control of the traffic. Flows can be described in the following ways: fine or coarse. Fine, as you would guess, deals with very precise flows. So in this example, we have 9 out of 10 tuples specified in one wildcard entry. Coarse flows are more broad, and in this example, 2 out of the 10 tuples are specified, and the rest are put in as wildcards. This would act much like route summarization would, which would come in handy when limiting the amount of entries per flow table. So how do we go about connecting OpenFlow-enabled switch to communicate with its controller or controllers? First, you start by configuring a port in the switch to be the path to the controller. This interface is not checked against in the flow tables, and the controller action in the flow table would send it to this port. Then each side will send an OFPT hello message with its highest supported version of OpenFlow. Then negotiation will happen to determine what version will be used between them, and if the connection is not successful, the recipient will reply with an OFPT error message. This OFPT error message will have a type field of OFPT hello failed, a code field of OFP HFC compatible, and an optional ASCII string explaining in data. Then the connection will be terminated. So what happens if a client loses its connection to a controller? Well, the client will then try to contact one or more of its backup controllers. If it can't get a hold of any controller, then the client goes into a mode known as emergency mode. The client will reset the current TCP connection and use only the emergency flow table entries. When they're added to the switch, they're tagged as emergency. When it enters into emergency mode, all non-emergency entries are flushed from the table. When the client can finally talk to a controller again, the emergency flows will still remain there. You can also specify if you want all flow entries to be flushed when it reconnects. But by default, all of the clients operate in emergency mode until a connection to a controller is established. So in a very high-level way, we can see how most of this initial integration works. We start here with an OpenFlow controller. We then add a few switches to the mix and get them to start negotiating their connections to the controller. Once a connection is negotiated, the controller will build its topology of the network from its point of view. Again, this is better than getting each individual switch's point of view. This is seeing more of a holistic view of the network. We will get into how this works by using LLDP in the next class, but for now let's assume that this has been done for us already. Next, the controller will update with clients with a flow mod or a series of flow mods, and then the clients will then take that information and update the FIP. And that, my friends, is the magic of OpenFlow. Pretty cool, right? So we haven't even begun to explore the real possibilities and the value of this protocol yet. So to recap what we've learned, we've looked at the switch operation, how it used its fib and TCAM, the three core SDN components, and how we would implement our state distribution. Now that we have this base knowledge, we can start taking a look at the specifics. So follow the lab for this class, get an OpenFlow controller installed, and how to attach a software switch to start playing with this. I hope this video has been informative, and I invite you to participate in the forum for further questions. And most importantly, nerd up for what we have in store next. Thanks for watching.